All right. So streaming should be on in a few seconds at the most. Yep, I'm double checking and it is on. So we are on air. All right. So I'm going to close my monitor. And it's time to get started. All right. All right. So we are going to start today, and today's main topic is going to be about the stack. I changed the order a little bit. I used to have compiling C control structures ahead of calling and returning from subroutines. Now these two topics are they're kind of orthogonal, meaning that they are independent from each other. I can choose to talk about one or the other one first without really affecting anything else because they have basically no dependencies. So that's what I'm doing, is to kind of change the ordering a little bit. So instead of talking about compiling C control structure, I'm going to talk about calling and returning from subroutines. And looks like there are no questions from the Discord text channel. All right, so we're going to continue with the discussion here. All right, so calling and returning from subroutines. This is one of the few places where I still have a module because at some point it becomes just kind of, you guys have to kind of take notes, instead of relying on my modules. All right, so right here we have a module that simply talks about calling and returning, calling a subroutine and how to return from a subroutine. I have a C sample program here for your, as an example, right? So here is an example in C. We have the main function as usual. The main function in a real C program is really just like any other function, except that there is startup code that would pass certain arguments to the main function. Excuse me. But since we don't have any parameters here, this main actually does not understand that it actually has arguments already passed to it, which are the argc, the count of arguments, argv, the argument values. So those are the things that you pass when you are running a command from the command line interface and you're specifying additional stuff after the name of the executable. So in this case, we're just completely ignoring arguments completely. And then we have two function calls. We have one function call to f on line 7 and another function call to f on line 8. And there's only one function f definition, which is from line 1 to line 3. Now obviously f is totally useless because it doesn't do a single thing and it does not return any specific value. So we are looking at this particular sample program because we just want to understand excuse me, the challenges of calling a subroutine and also returning from a subroutine. So Bernard put in a question in the text channel. So you can use those runtime parameters to start a program from bash with arguments. Yes, that's exactly what we did with the two exponent, positive exponent and negative exponent program, and also LogicSim. Now LogicSim is written in Java, but it's the same concept, the same idea. In fact, if you want to test that, you can just go ahead and make a very simple program. Just main doesn't do a single thing. Put a breakpoint in main, and then you run the program, in GDB. So in GDB, you can still do a run, R, and then a space, and then a bunch of stuff, and those would be passed in as the argv values, and then argc, which is the first argument, will tell you how many of those things we have on the command line. So they are very useful, for general programs. But right now we're just going to be focusing on the control part of a subroutine. In other words, how do we get to a subroutine, and how does the subroutine get back to the caller? So that's going to be our focus today. So do we have any questions about the topic that we're going to go over today, especially the C concept portion of it? All right, I'm not seeing any questions in the text channel, nor and nobody asked, using the voice channel either. So I am going to assume that we are doing okay with this particular sample program. So as the text in the module explains, this is something that we should already understand, because you should have learned how to write subroutines and how to call subroutines in CISP360. If you have not, we have a problem. So I'm going to assume that we already know how subroutines work in general. And then Mandeep is writing something in the text channel. So I'm going to wait a little bit until I see the question in the text channel. And we also have Bernard typing. Exam 2 is going to start during the lecture time. So it is 5:30 p.m. to not 7, but 6:50 p.m. because the duration of the lecture is only 80 minutes instead of 1 hour and a half. All right, so Bernard is asking, there's no way to overload the main function with different set of parameters. I do not believe so. In C++, you may be able to do it. I'm not 100% sure. In C, in regular C, you don't have overloading. There's simply no overloading whatsoever. So I'm not really sure in C++ whether you can or cannot overload main by specifying different types of parameters. Can we start at 5:28? Well, as soon as you get your test, you can start. I have no idea when you're going to get the test. I just know that it's going to be sometime before 5:30. So you can get started as soon as you can. So same format as exam 1, yes. Well, okay, format as in how the test is distributed, but not in terms of what kind of question you will see in this exam. Functions or subroutines are basically the same semantically, yes. So function is specific to C, so when people use C, they refer to subroutines as functions. In Pascal, functions are specifically subroutines that have a return value, and subroutines that do not have a return value are called procedures. In JavaScript, they are also called functions. So when you want to define a subroutine, it's called a function. And that also applies to both things that return a value as well as things that do not return a value. I'm just trying to think of what programming language uses sub. Visual Basic, for one, uses sub, and I think there are a few other languages that also use the word sub to denote the beginning of the definition of a subroutine. So basically, they're interchangeable. So if you hear me talking about function, procedure, subroutine, they're basically the same thing. All right. So moving right along, we are now going to get into a digression to talk about the stack. Okay. So the stack is basically a last in, first out type of construct. So one way you can understand the stack is to think about a U-Haul truck. Okay, so when you are moving or helping someone else to move, the first item that you put into the U-Haul truck is going to be the last item that you're going to remove from the U-Haul truck when you get to the destination, and conversely, the last item that you try to push onto the truck, and slam the tailgate before that thing falls off of the truck would be the first thing that falls off the truck when you get to the destination and open the tailgate. So that is what a stack is. It is basically a last in, first out data structure. Now, I do use the term data structure, but it is not in the same sense as in CISP310. So you do not need to have taken CISP310 to understand what LIFO means in the context of this class. It is simply last in, first out. All right, so it's time to practice a little bit of what last in first out mean. But before we get there, it is important to talk about two special terms. One is called push and the other one is called pop. So the term push is basically referring to we are putting an item onto the stack. Okay, we are storing something. You can think of it as you're putting something into a U-Haul truck. Pop, on the other hand, is the action of removing something from the stack. So given that context, or given the meaning of push and pop like that, I'm going to give you a few examples just so that we understand what push and pop mean. Alright, so I'm going to say, okay, this is an example. And in this example, we're going to do the following. We're going to push 23, and then we'll push, I don't know, 15, and then we'll pop into a certain variable. We'll just say var1. var1 is a variable. And then we're going to push again, and we'll push, say, 11 this time. And we'll pop again into some var2, and then we'll pop into var3. Alright, so this is just a thought exercise without any detail of implementation. So the question is, at the end of the entire thing, what is the state of the stack? Do we still have leftover items on the stack, or is it empty? And also we want to find out what kind of value would go into var1, var2, and also var3. So let's think about this, okay? So you can just kind of in your mind, you can have a little mental picture of a U-Haul truck. So you label a box 23, you put it into the truck. You have another box, label it 15, you put it into the truck. And then you proceed to remove the first item, that you see on the truck, and give it to a person called var1. And then you label another box, as 11, and then you put it onto the truck again. And then you remove the first item that you see on the truck, give it to a person called var2, and then you remove yet another item on the truck, the one that you can see right away, and give it to a person called var3. So the question is, who is getting which box? Okay, var1 is getting which box, var2 is getting which box, and then var3 is getting which box. That's the question. Now, conversely, okay, not conversely, but an alternative way to look at this is simply to use, slips of paper. So you basically write 23 on the slip of paper, put it on your desk, write another piece, write 15 on another piece of paper, and then put that piece of paper on top of the first one. And then you remove the first one, the one that is on top of the stack, and you give it to a person called var1, and then you write 11 on yet another piece of paper, put it on to that stack, and then you remove the top item to give it to var2, and then you remove another top item, what is the first item to var, and give that piece of paper to var3. So that's kind of the mental picture you can use to kind of imagine the operation of a stack, because we don't really care about the implementation of a stack at this point. We just want to know, in theory, what does it do? Alright, so we got a few answers. var1 gets 15, and var2 gets 11, and then var3 gets 23, and that is correct. And 6 people gave it the thumbs up, so very good. Max got the right answer, and so does Brian. Very good. And also Max commented that the stack would be empty because we have 3 pushes and also 3 matching pop operations. And we do not pop from an empty stack. Every time we pop in this example, there is at least one item on the stack. Alright, very good. So it looks like we understand the concept of pushing, which is simply to store an item onto a stack, and the action of popping, which is simply the action of let's remove something from the stack and give it to blah. Okay, because usually when you remove something from the stack, whatever you're removing is meaningful and you have to give it to someone. Not all the time, okay. When we get into what we're going to do for the rest of this semester, we'll find out that sometimes we don't really care about those items on the stack. We just want them gone, okay. But most of the time we do care about the value of the items that we have stored on the stack. All right, very good. Okay, so now we are going to concentrate on the implementation of, how do we put something on the stack, how is the stack itself implemented, and also, how do we push and how do we pop those items. So what we start with are the definitions here. Okay, so you can stack size can also be done using const. I'm just a little bit old school and use macros to define symbolic names like this. So stack size is simply a macro. So every time the compiler, actually the preprocessor, sees stack size, it understands, oh, it really is just the text in text. Okay, it is equivalent to just 32. So that means, in the next line, we are, allocating the space of 32 bytes, right? Because uint8_t is unsigned 8-bit integer, so we are reserving 32 of those things, and we call the array stack. Now, the name stack means nothing special. Okay, you can use the word stack, in a C program. Anywhere you can use a variable name. So the name stack has absolutely no special meaning whatsoever. I simply have an array of 32 bytes and it's called stack. Okay, so that's basically it. And then we also have SP, which is the abbreviation of stack pointer. So as a stack pointer, you can see it is not a unsigned 8-bit integer. It is a pointer to an unsigned 8-bit integer, because we can see how it has an asterisk here to signify that SP itself is not an unsigned 8-bit integer. It is a pointer to 1. So are we okay with these three definitions / declarations, and can we move on from here? All right, so Omir says we are good to go, and I don't see anyone saying we are not ready to go. So all right, cool, excellent, thank you. So now we are moving on, and the first thing we want to see is how do we push something on the stack. So as it turns out, the way we push something on the stack is a little bit counterintuitive. So the following code here is going to push the value of x on the stack. So the first thing we do is to decrement the stack pointer, and the comment here says it is for reserving space on the stack. And then the next one is to say, the location that I just reserved, now I want to store the value of x to the location that I have just reserved. So to understand why these two statements would implement what we already understand as pushing, you kind of have to understand how the stack is organized. So normally, okay, we are trained to think, okay, if you have an array, you filled up the array from index 0 and then index 1 and then index 2 and so on. Well, why? Is there a special rule in C and C++ that says you cannot start from the end of an array? No, there's no such thing, right? Once you have an array, as long as you're not indexing out of the valid locations of the array, you can store things in any order that you want. Okay, so in the case of using a stack in the system, we basically grow the stack in a reverse order. So given a stack with 32 bytes, okay, in this case, the location that has an index of 31, which is the very last byte, is the first one that we're going to use to store something. And then we move down to locate to the one at index 30 and then index 29 and so on. In other words, if you want to fill up the entire stack, the byte at index 0 is going to be the last one that you will consume until the stack has no room left. Now, why is it so weird like this? Well, there are reasons. Okay, so we'll get to the reasons, I would say in a few lectures. Okay, so it's not going to be right away, but in a few lectures we're going to do that. All right, so moving on, even though some of you may have some concerns and questions about why are we doing it like this, so for the time being, just kind of accept it, okay, and just say that, okay, this is how we allocate space and how we store something onto the stack. The second line here, this one is not mysterious. It should not be the mysterious one because this simply says, okay, whatever the stack pointer is pointing to is where I am going to store a value. The stack pointer, in a sense, is a bookmark. In other words, it is simply a bookmark that tells you which part of the stack is in use and which part of the stack is not in use. So all the locations starting from where the stack pointer points to and all the way up to the end of the stack, those are in use. And all the locations below where the stack pointer points to, those are not in use. So the stack pointer is simply a bookmark that tells you which part of the stack is in use and what is the most recently pushed item on the stack. So that's the job of the stack pointer. So how do we remove something from the stack? How do I take a particular value from the stack and then store that into a variable called x in this case? Well, as you can see, it is exactly the opposite of how we push something on the stack. And it's not really just that we are decrementing when we are pushing and we're incrementing the stack pointer when we are popping, but you can see the two statements are also opposite. In other words, when we are pushing, we have to decrement the stack pointer first, and then we store something to the location that the stack pointer is pointing to after the decrement. But when we try to remove something from the stack, we remove or we copy the value that the stack pointer is pointing to first, and then we increment the stack pointer. We got a question in the text channel. Is the stack pointer similar to labels that we have been using like L1? Nope, that is not the case. Okay, the stack pointer has its value being dynamically changed during the execution of a program. A label is an assemble time construct. You can kind of think of it as a compile time construct. In other words, once it has a value determined at compile time, or in this case at assemble time, that value cannot change when the program runs. For the most part, labels are very much similar to macros using the pound define. All it does is to associate a symbolic name to a numerical value, so that we, the humans, the programmer, we don't have to remember all those numbers. We just have to say, oh, okay, that location has an alias. It has a symbolic name, and I can refer to it much more easily as L1, label 1, or whatever you want to name the label. Alright, so one last thing, right? Because we have to initialize the stack pointer before we start to use it. So the initialization of the stack pointer is going to look like this. So the stack pointer is initialized to stack plus stack size. So if you have never encountered arithmetic done to a pointer, this is basically the same thing as this. So let me switch to the slide over here to indicate what how to write the initialization in a different way. So if you want SP equals to stack plus stack size is the same as SP is the address of stack, and then we use stack size as the index. So these two statements, or these two assignment expressions, are equivalent. So which one you want to use is entirely up to you. Okay, if you feel more comfortable with pointer arithmetics, you can use the first one. On the other hand, if you prefer to look at the stack as an array, and you prefer to look at indexing instead of pointers, then the second way is probably more intuitive to you. Alright, so we got some activities in the text channel. How would we make sure the memory between SP and SP plus stack size is all free? It is the opposite. Remember what I said. The stack pointer is the bookmark, and whatever is at the stack pointer and all the way up to quote-unquote the end of the stack, to the highest location of the stack, those are all in use. And that's why we initialize the stack pointer like this. But the question still remains, how do we make sure that those things are all free? Well, the answer is we don't. There's nothing to really check here to make sure that we are not underflowing the stack, meaning that when the stack is empty, that we do not attempt to remove something when it's empty. And the other way is to overflow the stack. Yes, I know you guys are thinking about Stack Overflow, which is actually part of the reason why we have the term Stack Overflow. So when your stack is already filled up, every single location is already in use, and you attempt to push one more item onto the stack, the code that we have talked about here has no checking whatsoever. It will simply pretend that the next location down or the next location up is still a part of the stack, which is exactly what assembly code is also going to do when you are trying to push something when your stack has no room left, or when you try to pop when your stack is already empty. So basically we'll just say that bad things will happen, but there's no checking. Alright, so Bernard said, if I recall, aren't arrays given the number of indexes plus a pointer in memory? Arrays in C is really just the starting point. There's no information about how large the stack is, unless you have a stack that is either statically allocated or it is an auto local variable. Then within a certain context, you know what the length of the stack is, but outside of that context, it simply becomes a pointer. And this is one of the reasons why C and C++ in general are awful programming languages, because it cannot track the number of items of a stack of an array, any array, not just in this context. In all succession, indexing all the way. Alright, well, it's up to you, but I am going to use the dereference symbol, which is this item over here, because it's a pointer. SP is a pointer, and as such, you cannot use indexing with a pointer, because we want to get to what the pointer is pointing to. Now, that is not true either. Okay, I just lied, because I'm not sure whether this is helping or gonna make it even more confusing, but I'll put it here anyway. So if the expression of asterisk SP is really the same as SP bracket 0. So these two expressions are exactly the same. They mean exactly the same thing. It's just that one looks at SP as a pointer, and you're using dereference to look at the location that SP is pointing to. The other one looks at SP as quote-unquote an array, and you're accessing the first item of that array. I personally would use the first one and just totally avoid the use of indexing. In other words, let me point out which one I am going to prefer. I am going to use, I'm going to use the first one, which is this part here, and I would avoid the use of the indexing operator, because that is just going to add to confusion. That's completely up to you, Chris. I just want to point out that LD and ST instructions, they do not look at things as an array. Now you can kind of force your way in and say I prefer to look at everything as an array, which is okay, because the entire memory space can be seen as one gigantic array. But it is not how I am going to describe the operations. So there is that. Alright. So now that we have looked at how we push, how we pop, how we initialize, and also how we allocate for the space on the stack, the next question is, well, this stuff is all written in C, so how do we do the same thing in assembly language, in TTP? So in TTP, the way we store something, the way we push something, and the way we pop something is a little bit mysterious. There's no single instruction to push, and there's no single instruction to pop. Some of you may know the x86 architecture, and in that particular architecture, there is a push instruction and there's a pop instruction, which make things very convenient. And I intentionally did not use push and pop. I intentionally did not implement push and pop in the instruction set of TTP. Why? Because I want you guys to really understand what it is. Okay, what is push and what is pop? If we just go ahead and use those instructions, push and pop, then that detail is hidden. Okay, once the detail is hidden, it's very easy to have a misunderstanding of what is a push versus what is a pop, and that is why in TTP there's no such thing as, oh, this is how we push or this is how we pop. Alright, so what I'm going to do now is to take a look at the example that we have here, and we are going to change it a little bit so that we can actually implement this in TTP. So this way we can actually start to visualize how things are actually done. So instead of R1, we're going to say register B. Instead of R2, we'll say register C. And here instead of, oh, okay, I cannot, okay, fine, this is going to be register A, this is going to be register B, and this one is going to be register C. Now there's a reason why I'm avoiding the use of register D, because there is no such thing as a stack pointer. Okay, TTP text-to processor has no dedicated register as the stack pointer. Some of the architectures do. Like the x86 architecture does have a register that is dedicated as the quote-unquote the stack pointer. So when you use push, pop, call, return, those instructions implicitly would use the stack pointer as the register that is acting as, guess what, the stack pointer. But TTP has no such thing. So by convention, I am just going to say I'm going to use register D as the stack pointer. Alright, so it is really just a choice that I have made and go like, okay, out of the 4 registers, I'm going to have to use one of them as the stack pointer, and then just choose to use register D as the stack pointer. Alright, so now we have to look into all of those things that were written in C, and we'll think about how to do all of that stuff in TTP ASM. So we'll go back and revisit all the things that we need to do. The first one is in C code we have to define the size of the stack. Well, we're going to save that. We are not going to do that with assembly code. We're going to say whatever is left over that is not code, it's going to be the stack. So as you might know, when you are writing code in TTP ASM, the instructions are starting from location 0, and then it moves on to location 1, location 2, and so on. And I can just give you an example here too. I still have an example. So this is the sample program that I did for the absolute value. And when you look at the assemble tab, it shows that the last location, which is the halt instruction, is at location 09 in hexadecimal. But you can definitely tell that it fills up the memory content from location 0, and each instruction is contiguous to the one before, and we just ended up, in this case, we're using 10 locations. And yes, you're looking at 09 here, but remember we started from location 00, and that's the reason why we are using exactly 10 locations in this program. And those 10 locations are specifically location 0 all the way to location 09. All right. So what about the rest of the memory space? What about location 0A all the way to location FF? Those are, well, actually not used, right? Nobody has claimed ownership of those locations, and they're just going to be sitting in the processor doing absolutely nothing from the perspective of this specific program. Alright, so if those locations are not doing anything useful, might as well just use all of those locations as our stack. In other words, we are using the portion of the RAM that is not used for code, for instructions, opcodes, immediate values, and so on. The rest, we will just say that's our stack. So that's why, in implementation, we do not actually need to specify the size of the stack. It's basically whatever RAM is left over is the stack, and whatever. So we don't know ahead of time what size it is. It depends on how much code you have to use. How much space is used by your code, and the rest are basically the stack. And we don't need to allocate either. We simply say, well, it's going to be whatever is after the last byte that we use for the opcode, and the rest of RAM is stack. So that's why we don't need to declare that. And we don't have to declare a stack pointer either, because what I said earlier was, by convention, we're just going to use register D as our stack pointer. So these three lines have no equivalence in assembly code in TTP-ASM, because these are either assumed, or they're just basically going like, okay, whatever is left over, we will take all of that as our stack. All right, and Omer was typing something. I'm gonna wait until he's done. Oh, there we go. To be clear, this is something that is specific to TTP only. I wouldn't say it's specific to TTP. Most of the smaller processors would allocate the stack in the same way. So when I say smaller processors, I'm referring to the 6502, the 8080 processor, and so on. They basically they will follow this same convention. They basically say, okay, at the end of the entire memory space, that is quote unquote the end of the stack, and then whatever space is not used by static variables and the code would be the stack. Now sometimes you have to allocate a chunk of that as a heap, but basically the heap is going to be right next to code, and the stack is always starting from the end of the address space, or most of the time it starts from the end of the address space. So this convention is not unique to TTP-ASM, and not unique to the way that I use the memory space. Now remember, this is a convention. The architecture itself does not dictate whether we can use a stack or we cannot use a stack, or where we allocate the stack, and so on. This is just a way of using the space that is available. All right, cool. All right, so moving on to these two instructions, or these two statements in C, and now we want to say, okay, but how do we decrement the stack pointer when the so-called stack pointer is really just register D? So let's check it out. Okay, so I'm going to type out something over here. So I'm going to put it under push here. So under push, we have two things we need to do in C code. So in C code, the first thing we need to do is to decrement the stack pointer. Now, because we are not using the value of the decrement, so that means you can use pre-decrement or post-decrement. No one cares. Okay, it means exactly the same thing. And then we say whatever the stack pointer points to is going to be used to store a specific value. So we'll just say, okay, V is representing the value that we want to store. And because this is C, we need a semicolon to end the statement. So this is what we want to do in C. So now the question is, how do we do the same thing in TTP-ASM? All right, so first thing first, the first thing is to decrement the stack pointer. So remind me again, what did I say about which register I'm going to use by convention as the stack pointer? Hopefully somebody took note. All right, you guys are good. Okay, so we know register D is our stack pointer. Decrementing a pointer is really just decreasing it by 1. So how do we do that? Which instruction do we use to decrement register D? In other words, we decrease the value of register D by 1. So you can look up the opcode table and find the one that says decrement. I think I just gave you the answer. Yep. Yep, I did. I just gave you the answer. It's just decrement D. Okay, so this one is going to, And I'm just going to put in some comments here. This is going to be the same as minus minus sp, decrementing the stack pointer. All right, so the next item is how do we store something into the location that the stack pointer has? Now this one is a little bit tricky, so we can say assume value v is in a specific register. We'll just say it is in register C. Okay, so assuming the value that we want to store, that we want to push on the stack, is already in register C, then what do we need to use? What instruction do we need to use in order to store that specific value to where the stack pointer is pointing to? Almost, Omer, almost. Remember what the parentheses are for. Yep, exactly. So the parentheses are nothing more than eye candy to emphasize that whatever is enclosed in parentheses is the one that is being dereferenced. So the actual instruction is going to be stdc. There we go. All right, very good. And Bernard even figure out the bit pattern. I'm not really sure that's the right bit pattern. So let's check it out. Okay, so if we want to do stdc, what would be the bit pattern for the opcode itself? So let's go ahead. Oh, you guys are good. I can see a bunch of you already over at the opcode table. So that is smart. That is the way to do it. All right, so STYX. Okay, so register D is the YY, and then register C is the XX. So it's going to be 1111. The most significant 4 bits would be 1111. Those do not change. And then XX is going to be 10, and then YY is going to be 11. So we have 1111, which is F in hexadecimal, and then we have 1011, which is a B. So we have FB as the opcode of ST in parentheses D, comma C. So there we go. Oh, for decrement D. Oh, I see. Okay, I did not understand that one. Yes, so for decrement D, it is going to be 1110, which is what Bernard has, and then XX is register D, except it has to repeat itself, because remember, we stole this bit pattern from somebody else. Does anyone remember whom do we steal this particular opcode family from? We robbed a certain family of instructions to get this one. I'm not sure whether it's okay, let's find out, right? I mean, we can just kind of look up the column here and see which one has 1110. So it turns out to be CMP. So those of you who answer CMP, you got the right answer. So we hijacked certain opcodes from CMP because it makes no sense to compare a register to itself. Because the end result is very predictable. If you subtract a register from itself, the Z flag is going to be set and all the other flags are going to be cleared. So why would you want to do that if it doesn't serve any purpose, right? So since it does not serve any real purpose, we are just repurposing. That's the right word these days. So we are just repurposing the bit pattern for a useless CMP instruction to do something else. In this case, it is for decrementing a specific register. So there you go. And then increment stole it from somebody else. So increment stole that from whatever starts with 1101. So that would be the OR instruction. So the OR instruction, ORing a register with itself, which doesn't do anything useful except for touching the sign flag and the Z flag, which sometimes is useful, but we got AND doing that already. Nobody's stealing anything from AND. So because AND AA and OR AA basically do exactly the same thing, so we just need one of those two. So since we are keeping the AND family intact, so now we are basically hijacking 4 of the bit patterns of the OR family in order to specify decrement instructions. So there you go. All right, very good. So I hope you guys are relating what we are now talking about to something that we talked about earlier in one of the labs. Alrighty. So now we have the whole thing, right? So we have decrement D followed by stdc, assuming register C has the value V that we want to store. So if register C does not, then you have to initialize it first. So you're going to use the LDI CV, V being the actual constant value that we want to push on the stack. So you're going to need that prior to the ST instruction if register C has not been initialized yet. Alright, so let's check out what pop is going to do, or how we're going to implement pop. So the first thing we need to do with pop in the C code is to say a particular register is going to get whatever the stack pointer is getting. Okay, so in this case, let's assume that we want to store whatever the stack has. Okay, the item that was just pushed to register B. Okay, so what do we need to do if we want to pop the top of the stack? Top of the stack means the most recently pushed item. So if we want to pop the value into register B, what do we need to do? This looks like the opposite of the store. So what instruction is opposite to store? It's the opposite direction, by the way. No, but that's something we need to do after this. Okay, so we need to dereference a certain register, get to the location of a certain RAM location, and then take that value and then store that value into another register, possibly. All right, LD is the correct answer. Okay, so we have LD, and since I said register B, that's how we pop, the a value from the stack to register B. And then, okay, now we are ready to do something else. Okay, now we are ready to increment the stack pointer. So to increment the stack pointer, we are just using the increment instruction. Okay, so increment D is the way we increment the stack pointer, because we basically use the convention of using register D as our stack pointer. All right, so looks good. So what we're going to do now is we are going to take a look at this specific sequence of pushing something, popping something, and so on, and we're going to implement it in TTP ASM. Okay, so we're going to take a look at this, and I am going to specify the code at the bottom of the screen here. So I'm skipping a bunch of stuff for the time being because I need to put in the code. And the funny thing is, well, not funny, but I actually put in the syntax highlighting of TTP-ASM into the syntax highlighting extension of NVIN, so it would actually be highlighted as I type, which is handy. It's nice. Alright, so the first thing we need to do is to initialize the stack pointer. Remember what we said? The stack pointer is supposed to be initialized to the very last location of RAM. Well, I kind of lied. Okay, so we would say, looks like it's going to be something like this, right? And by the way, the immediate value can only be in base 10, unfortunately. So FF is not a way to specify the same value. 255 in base 10 is FF in hexadecimal. Okay, but I lied. This is not what we want to do. Okay, because if we initialize the stack pointer like this, it means location 255 will never be used to store anything when we push things on the stack. Because remember, the first thing we do when we push is we decrement the stack pointer. So if the stack pointer was initialized to location 255 to go to that with the address of 255 in RAM, the decrement is going to decrement to 254 before we actually store to the location the register D is pointing to. Now, I know you guys are thinking, so what? We are just wasting 1 byte, okay? I got 16 gigs of RAM, or 32 or 64 gigs of RAM on my gaming computer. 1 byte is a drop in the bucket. Who cares? Well, we don't have that luxury when it comes down to TTP, right? Because we only have 256 locations for the entire thing. So wasting 1 byte, that's a no-no. So what do we do so that we don't waste that one single location? Someone is going to say, oh, we just need a +1 to it. Well, this brings us to another thing that is kind of important. You can use an expression when we want to express an immediate value. So anything that ends with an I, expects an immediate value. So does byte. But this is an infix notation. Infix notation means the operator is between the values that it's supposed to work on. In this case, we are trying to add the values of 255 and 1. So 255 and 1 are the values that we want to work on, and then the plus is the operation. And this is called infix because the operation is between the values that we wanted to work on. And this is something that we learned from, I don't know, elementary school, I guess, right? So we have been poisoned by infix notation for many years. So in the case of myself, I have been poisoned for more than half a century. So the way we do it in TTP ASM, the assembler understands postfix notation, which is basically saying, tell me the values first, and then I'll operate on those values. Okay, so you have to specify, okay, here's one value for you, 255, and here's another value for you, 1. Okay, so what am I supposed to do with these two values? Oh, by the way, just kind of add them together. So that's why in postfix notation, 255 plus 1 is 255, 1, and then the plus. This is called the postfix notation. So I look at this and go like, wait, hold on a second here. 255 plus 1. Now, yes, I did say it in infix notation way. But isn't that really just 256, right? It's 256. So we can, should be able to say, okay, so why don't we just say it like this, okay? Why do we want to waste assemble time, to add 1 to the constant of 255? Well, yes, that is correct. Okay, we really can save that little bit of time for the assembler. But 256 has a problem because how many bits do we need to represent 256? Assuming exactly, so Eric is quick. 9 bits, okay? And the processor has each location is, and also the registers are only 8-bit wide. So that means we really cannot store 256 into register D. Except we can, because remember the modulo stuff, the modulo math thing. So we are just looking at a value like 256 and go like, okay, so if we mod this value with 256, what do we get? Can someone tell me what is 256 mod 256? Yep, Bernard is quick. It's 0. So it really means exactly the same thing if we were to say LDID 0. This is how we initialize the stack pointer. It sounds really it doesn't sound intuitive at all, right? Because I kept saying, oh, the stack is going to start at a very, very last location of RAM, and here I am initializing the stack pointer to 0. But it's not, except it's not wacky at all. Okay, this is not hacky, it's not wacky. This is actually, it makes sense. Because what happens when you subtract 1 from 0 using an 8-bit pattern? So we are not even bothering with, oh, is it signed or unsigned? I'm just asking you what is the bit pattern of 0, 0, 0, 0, 0, 0, 0, 0 minus 0, 0, 0, 0, 0, 0, 0, 1. What is the bit pattern? What is the difference? Exactly. So Eric is correct. It is 1111 1111. Now the pointer, when you use that bit pattern to specify when you present that bit pattern to the A port of RAM, it doesn't care whether it's signed or not. All it does is to say, okay, do we have a location matching 1111 1111 as a bit pattern? Yes, we do. Okay, so it just goes, it just addresses, or it points to that location. All right, so this is how we initialize the stack pointer. Very good. So now we are going to go back here to say, okay, what do we need to push? We want to push 23. So the way we push 23 is there's no easy way to do it. Okay, for those of you who know the Intel instruction set, you can literally just go like, push 23. That's one instruction in the Intel notation. But you can see how push is not highlighted because it's not an actual mnemonic in TTPSM. So we're gonna have to do it the kind of clumsy way. Okay, the clumsy way is to say, oh, we have to put it into a register first. Now you cannot use register D anymore because it is the stack pointer. No, register A, B, or C would do here. So we can put it into register A, and then we use this to push it on the stack. Let's see, what else do we want to push? I'm reading from my text here, so I can show you what I'm reading so that you guys can go like, oh, okay, so that's why you don't need to flip-flop or scroll the window here. So the next thing we need to push is 15. Okay, so we'll just kind of copy these two lines, change, oops, okay, pop, oh, there we go. So now we change the 23 to a 15. And then we need to pop something into register A. So to pop something into register A, the first thing we do is to do a LD instruction. So LD register A from where the stack pointer is pointing to, and then we increment the stack pointer. And then the next thing we do is to push 11 on the stack. So now we kind of need to do the same thing, LDI, except register A is quote-unquote occupied now, so we can use another register. Let's use register C, because register C won't be needed until the very end of this sequence. So we can just kind of put it into register C. So we load 11, the value, into register C, and then we store that to whatever the stack pointer is pointing to, except I forgot one thing, didn't I? I forgot to decrement the stack pointer first. So some of you are looking at line 43 and line 44, these two lines here, or these two lines over here, and go like, but Tech, isn't that kind of stupid? You just incremented a register and then you decrement again, they kind of canceled out each other. You will be correct. They do cancel out each other. However, they are doing things from a different context. So even though if you really want to optimize, you can actually just comment out both the increment, this increment here, and this decrement here. But I'm going to keep them here because they represent parts of different operations. This part here is the beginning of push 11, and then the other one is part of pop to register A. So that's why we want to keep them separate, because we want to keep both increment and decrement here because they are parts of two different logical operations. So even though you can do an optimization to get rid of both the increment and the decrement here, that would basically make it harder to understand what we are trying to illustrate here. All right. So with this out of the way, what is the next thing we want to do? So right here, we want to pop into register B. So that's pop B. So to pop into register B, we basically do the LD instruction first, LD BD, and then we increment the stack pointer. And then finally, we want to pop into register C, which is LD CD, and we increment D again. So since I'm commenting, might as well just start from the beginning. So we have initialization of the stack pointer, and then we have push 23, and then we have push 15, pop A, push 11, pop B, and then a pop C. Alright, so we got a question. Aren't we missing decrement D for the first two push operations? And you are correct. Eric is correct. So since you guys spotted my missing something here, the question is now, where do we put that decrement D? So can someone point out between which two lines we should insert the first decrement D? Yep. Well, comments are useful because this is what they are supposed to do. I highly recommend all of you to comment your program as well. Before the LDI, well, we have some choices here. So there are several ways we can do it. As long as it is before the ST, will still be okay. So the last place to put it is over here. So we need a decrement D latest by this time, but we can do it before the LDI as well. And then the second one is kind of the same thing. We have to do it before the ST instruction, but we can do it here, before the LDI instruction, because these two do not interfere with each other. So we are looking at these two instructions. They're not interfering with each other, and as a result, their ordering does not really matter. And the same thing over here. Okay, these two operations do not interfere with each other, so you can do it in this order or in the reverse order. It doesn't really quote unquote matter. All right, very good. So now we got a program, and we want to find out what is going to happen when we run this code. So let's go ahead and put a halt instruction at the very end here, and then we'll put a no op instruction at the very beginning, because that's what we need in order to use the command line way to run Logisim. Alright, so we got another text entry. So when we are doing LDI A23 and LDI A15, we are storing them at different addresses. Actually, LDI does not store anything. LDI is loading a constant into a register. A register is not a part of RAM. In other words, a register does not have a location associated with it. We just specify, is it register A, B, or C, or D? So there is a register specification which is built into the opcode itself, right? Because the XX and the YY, when we specify the bit pattern of the opcode, that is how we designate which register we want to use. But nonetheless, a register is not a part of RAM, so it's not a location. All right. Cool. Now, obviously, I'd like to talk about things that can potentially be confusing. So there are processors out there which basically merge the understanding of RAM and registers. Yes, isn't that confusing? So RAM location 0 is also a register. RAM location 1 is also a register. So basically, they look at the first, in this case, the first, I think, if I remember correctly, the first, I want to say 32, but I'm not 100% sure. So let's just call that 16. Okay, so the first 16 location of RAM is they're also corresponding to the first 16 registers in that specific architecture. So there are some architectures that would use an aliasing mechanism so that you can refer to the same thing, whether you refer to it as a register, hey, that's cool, or you can refer to it as a memory location, that's cool as well. Okay, and so those are kind of special type of architectures. The TTP does not do that. The TTP has a very clear distinction between what a register is and what a RAM location is. So those two are not interchangeable. All right, so it's time to run this program. So I am going to do some VI magic, get this program to just this portion here from line 17, no 20, 37 to 61. Okay, so 37 to 61, and I'm going to use it to overwrite a file that we would call stack.ttpasm. All right, so we do have that code written into that location, so now I can show you what that looks like now. So we'll take a look at tmp stack.ttpasm. So this is the program that we just wrote, and now it is its own file. So now we are ready to trace it. And this is, I personally think it is really helpful to be able to run that submit script basically from anywhere. So I can run it from here. I just have to supply the full path because I did not make an alias in my bin folder. So it's under Documents, CISP310, River Spider, Submit, and then the name of the file, which is /temp/stack.ttpasm. So now the program, the script is doing its magic thing, so I don't have to do this by hand. Okay, let me just read the text carefully. So it says right here, submitting to assembler. Okay, assembler finished, validating object code. Object code is good. Starting simulator. Simulation finished. Submitting trace data. Trace data uploaded. Check the analysis sheet. Woohoo! So now we go to the assembler sheet, and specifically we want to go to analysis. Okay, and you look at this and go like, what are we looking at, right? Well, we are looking at the effect of the pushing and the popping. Specifically, we want to know what is being stored into registers A, B, and C. Did we put the right values into A, B, and C as the way we specified it earlier when we performed these operations by hand? So if you guys use the text channel, you can scroll up and find the correct answer, because most of you actually found the correct answer. So register A is supposed to be 15, register B is supposed to be 11, and then register C is supposed to be 23. So that's what we're looking for. But remember, we have to convert everything in hexadecimal. Alright, so we are just looking at register C first. So this is the nice thing about the trace, is you can read it forward, you can also read it backwards. It is every single row is representing a slice of time, and as a result you can go forward, you can go backwards, except it's not circular, right? Alright, so C has 17 in hexadecimal. That's 16 plus 7, which is 23. So that's good. That's what we were expecting. Register B has a value of 0B, which is 11. Yep, that's good too. And then we want to look for register A. The last time we update register A has a value of 0F, which is 15. So we got the values into those specific registers in the right order. What is also important is to note how the register D, the stack pointer, is back to location 0, back to the way it was initialized. So we are now going to call and say that, oh, the stack is balanced, okay? Because the stack pointer, once the stack is empty, the stack pointer goes back to point to location 0, 0. So that is also important to check to make sure that your program does not have any leftover stuff on the stack when it's done. Cool. Any questions before we actually get into the calling and the returning of subroutine? Because that's going to be what your lab is about. So we want to be able to finish that discussion as well. But they are based on pushing and popping first, and that's why the first thing we need to do is to talk about pushing and popping, and then once we understand what is push and what is pop, what is a stack, then we can talk about how to call and how to return. Alright, I'm not seeing any questions. Then we're going to move forward with the module and talk about how do we call and how do we return. So calling and returning is kind of interesting, because let's go back to the C code that I was using for illustration purposes. So you can see how main is calling F. The first time we call F, we just have to continue execution in the body of the definition of subroutine F. When F is done, it's easy to continue execution over here with the second call. So some people would say, oh, JMPIs can do this, right? JMPI can go from any location to any location, so that's great. And it can also go from any location, meaning the end of the subroutine, to the next place in the caller. But the problem is, if you use a JMPI here, on line 3, then it is fixed. Okay, JMPI can only go to a specific location. That location has to be determined at assemble time. The first invocation of F is supposed to return to line 8, but the second invocation of F is supposed to return to line 9. So now we have a problem, because how we continue execution at the end of an invocation of a subroutine kind of depends on where it was called from, right? And with using JMPI, we cannot handle that type of dynamic return address, okay? Because sometimes we the first time we call f, we have to return to line 8. The second time we call f, we have to return to line 9. So we cannot use a JMPI to get back. A JMPI is fine to get to the subroutine, but it's not okay to get back to the caller. So now the question is, how does this have anything to do with the stack stuff that we just talked about? So as it turns out, the stack is useful because before we continue execution at the definition of f, the caller is going to say, I'm gonna drop a hint to the callee, the subroutine being called, and I am going to use the stack to communicate where the subroutine is supposed to go back to when the subroutine is done. So in this case, when f is done with doing absolutely nothing, it's going to use the stack. It will count on the stack and count on the fact that the caller has pushed what we call a return address on the stack. So it can continue execution to where the caller says, when you're done subroutine f, this is where I want you to continue execution. All right, so I am going to do this. So I will kind of show you the so now I have to kind of increase the font size a little bit, so you guys can see the code more easily, because it is actually important. And I might need to turn off my webcam. Nope, I'm good. All right, so we are gonna look at call return.etp-asm. So the reason why I'm doing it like this is because I want to keep the C code on one side, and then on the other side I use my Vim here to work on my assembly code. So the assembly code, I'm going to keep the order of the definition of the subroutines. So the way we define the subroutine, is simply to use the name of the subroutine as a label to mark the entry point of the subroutine. So f has an entry point, main also has an entry point. So the first instruction, if I want to trace this code, I need an OOP to begin the entire program because of a certain bug in LogicSim. So the next thing we need to do is to initialize the stack pointer, right? So LDID0 is going to initialize the stack pointer. And I need a JMPI to main, because without the JMPI to main, the next instruction is going to be the first instruction of f. And that's not what I want to do, because I want to get to main first, and the main is going to specify what it wants to do, which is to call subroutine f. Alright, so now we're in subroutine main, and the main subroutine wants to call f. Now don't write this down if you're copying anything or writing notes, because there will be some editing involved. So we know that JMPI f is going to continue execution at the subroutine f. Now obviously there's some stuff over here as the body of f, but we are not concerned about that at this point. So so we know that JMPI f is one of the things that we need, but we also need to tell function f, okay, the subroutine, where it is supposed to return to. So now what we need to do, So now what we need to do is to say, okay, so let's use LDI register A, and we'll specify where the subroutine is supposed to return to. Now I'm just going to say return address 1 for the time being, and we're going to push it on the stack. In other words, we're looking at the stack as a handy place to store something. So to store something on the stack, we decrement D and then do std and then the register that contains the value that we want to store. So now the question is, where am I supposed to define return address 1? Because return address 1 is essentially a label, so that we don't have to do the counting to find out which location the subroutine is supposed to go to. So if you are to decide where, in terms of line number, to define return address 1, where would you define that? Where would you define return address 1 with a colon as the place for the subroutine to continue execution? All right, so, oh, there we go. Line 12 is correct. Okay, so Eric has gotten it. So return address 1 is supposed to be defined here. All right, so I know main is not done, okay, but we can go ahead and finish main first. So now we are ready for the second call. So the second call is going to start with something like this again, except we cannot use return address 1, because if we used return address 1, then the second call to F will also return to the same place that started the second call, and becomes quote-unquote an infinite loop. Even though it's not exactly a loop, it becomes infinite. So we cannot use return address 1. We're going to say, okay, let's define it as return address 2. But we still have to save that return address on the stack, which means we have a push on the stack. And then we continue execution in the subroutine. And just like the first one, this is where we want to define return address 2 as a label. So now we have looked at everything, and when everything is done, we can halt here, because there's nothing to do after the second call to F. There's no equivalence of return 0 from main when we are talking about the assembly code. So in assembly code, when we are returning from main in C code, it's basically just a halt instruction in TTP ASM, because it simply means, oh, okay, this entire program is done. There's nothing else to do at this point. Alright, so this is from the perspective of the caller. So from the perspective of the caller, it has to store the address for the callee to continue execution when the callee is done. So now we get to the callee and we say, well, since this is basically an empty void function, so we're going to use a single no-op instruction just so that we have something here to basically say this is what the subroutine is supposed to do, which is nothing. But now the subroutine is saying, okay, I'm all done. I'm ready to go back to the caller. What am I supposed to do? Where am I supposed to go back to? Well, remember these instructions, from line 10 to line 12 is a push. From line 16 to line 18 is also a push. So, how do we call that operation to retrieve something that we have pushed earlier? Just a term to refer to. Exactly, we are going to pop something, right? Alright, so we know how to pop something, so we can choose one of the registers to pop into. So right now, as long as it is not register D that you're popping into, it's going to be okay. Okay, so we're going to pop into register A, register B, or register C. Doesn't matter which one, we'll just pick register B. Okay. Alright, so the pop sequence is to do an LD first, right? So we have to use an LD, and then we use register B. In this case, just randomly pick one of the 3 that we can use. So the first one is an LD, and then we have to do the increment D. Okay, so don't forget to increment the stack pointer, because once that location is now retrieved, quote unquote, that location is not useful anymore. It's time to move the bookmark up by 1 byte to basically say, by the way, this location is no longer in use. We can use it again if we need to. Okay, so now the question is, what am I going to do? Okay, we just pop the return address. So right now, register B is going to have the value of the label return address 1. If it is if this is being done after the first call. Or it's going to have, register B is going to have the value of the label return address 2 if this is at the end of the second call to function F. So the question is, what am I going to do with register B? What we want to do with register B is something like what Eric just typed in the text channel. So I'm going to put it in comments here. So we want to somehow continue execution at the location that register B is pointing to. Okay, that's sort of what we want to do. So most of you are thinking, oh, we can just use a JMP-IB, but that's not going to work. Okay, it's not going to work because when the assembler is assembling JMP-I and then a B, it would assume B is a label. Okay, it does not understand B is a register, because a register cannot be used in a JMP-I. So since most of you are already on the opcode table, can you find a way so that we can just say, the quickest way to do this is simply to say, let's just copy whatever the register B has to the program counter, because guess what? The program counter is dictating which location we are going to use to get the next opcode. So by changing the program counter directly, we are changing the flow of the execution of the program. So it's JMP B without the I. Yes, so you guys are right. Okay, so specifically Dylan is correct. So it's just JMP B without the I. So you don't want the I because it's not immediate. This is using a register in one of the 4 registers, A, B, C, or D, to update the program counter. So that is what we want to do. Alright, so the program is now done, and I know I'm going a little bit over time, but we want to kind of watch this program do its little magic thing too, right? Because otherwise we just write some code, and if I had made a mistake like I did earlier, forgetting to do the decrement, that would not have shown. So we want to run this program. So we're going to reuse the command that we used earlier, and this one is call ret.ttpsm, call return tt.ttpsm. So we use the script to do whatever it needs to do, submitting the code to the assembler. It's good. Okay, we're simulating. Simulation is done. And now when we get back to the assembler, and we use the analysis tab, the analysis tab, we can now see how the program got things done. Okay, now this is really useful because at this point of time, to quote unquote study, it's not going to be just reading the notes. Okay, reading the notes is fine. Okay, you're reading what I just pointed out today, this part here, it's okay, but those are really just words. Okay, I personally would find the trace to be far more helpful. Now you look at this and go like, but I have no idea how to read this. You gotta be patient. Okay, you have to basically understand what each column is representing. Column A is representing the address of the opcode that we're executing. Column B is indicating what location of RAM is being read. Sometimes it's not relevant, but most of the time it's actually useful. Now column C and column D are particularly useful in this case because column C is indicating writes to RAM. Okay, which location of RAM is being written to, and what is the content that what is the value that we just stored into that location. So star FF equals to 0F. Basically what that means is we are storing the bit pattern of 0F to the location of FF. So I'm using the C notation. Asterisk means dereferencing. Column D is also useful because it tells us what we are doing with the registers. What kind of value are we putting into a register when the instruction executes? Now in this case, column E is useless because we are not changing anything with the flags. So nothing of this entire program would actually change the flags in any way. So for this specific program, column E is basically useless. But for other types of program, when you need to do calculations or compare, especially, the flags register is going to be super useful when you need to make decisions. Okay, if this is less than this, we want to go to that location. That's when the flags register becomes useful. Alright, so I am done with presenting all the information and all the knowledge that you need to know. Some of this is actually repeated in the lab itself. Okay, so try to be patient and read through all not only the instructions but also the explanations in the lab as well, because it's basically repeating a portion of what I just did in today's lecture. Cool. So now we're gonna release the lab, which automatically answers the question for certain people, do we have a lab tonight? The answer is yes, we do have a lab tonight. So I have just collapsed the other ones because it's just making the I don't want to have to scroll and scroll and scroll to get to certain things. So we have stack operations. You cannot see it yet. Okay, so once I release it, you can see it. Alrighty. Now, if I have not done this to some of the earlier labs, just remind me to do it, because I want to make sure that you guys can see the correct answer at the end of the lab activity, because this way you can use it for studying purposes as well. So it's going to be, it will show the correct answer at 9:50 p.m. and it's automatically today, I think. Okay. The passcode or the access code is LIFO, so I'm going to copy and paste it into the text channel. And it's going to do at the usual time, which is 9:50 p.m. See, this way it does, fill in the date. But if I try to do it over here, it does not seem to, backfill the date. That is interesting. So April 5th, 9:50 p.m. Oh, it wants the other format, does it? 2022 04 05 9:50 p.m. I'm not sure whether it's going to take this or not, because it looks like it wants a different format. Alrighty. I'm going to give it a try to save and publish and see if it can take that. Okay, so you guys can give it a try and see if you can get into the test. Nope, it wants to release it at the wrong time. Alright, so let's see if that works. Alright, so this time it does work. So it wants to specify the date using the at word to specify the time, and then the other one does not. What is going on here? In Canvas, what? There's no consistency of how to specify a time and date. Alright, so it's all good. You guys can get to it now. Alright. Alright, so I think we are done with the lecture now. So I am going to sign off from the voice channel and also